This QR code has an 11 by 11 white block covering its center. Yet in our fixed version 3 test, 2 different decoders returned the exact original message. The missing region spans 121 module positions. So where did that information come from? It did not come from a hidden copy of the picture. A QR code is not a photograph that a reader recognizes by resemblance. The grid carries function patterns, encoded data, and mathematical recovery information. If enough of the right information survives, the reader may reconstruct damaged code words. This is also a different system from the EAN13 barcode in the previous story. That retail symbol uses a final digit to test a decoded number. QR code can add many recovery code words, so some damaged bytes can be reconstructed. Detection and correction are different jobs in both stories, but the mechanisms are not interchangeable. Correction cannot begin until the reader finds the symbol. The 3 large corner patterns help locate and orient a standard QR code. A clear, quiet zone, 4 modules wide, marks the outside boundary. Cover, crop, or blur the wrong structure, and the reader may never obtain a usable grid. Once found, the symbol still has to be sampled. Version 1 begins at 21 modules on each side. Each later version adds 4 per side. Our test uses version 3, so its symbol grid is 29 by 29 modules before the quiet zone. The reader maps those module centers, rather than treating the square as one continuous image. The symbol also carries settings that tell the decoder which correction level and mask were used. The mask changes the visible pattern to improve readability. Then the decoder reverses it. Only after those steps can an implementation extract the sequence of code words and group them for correction. A code word is 8 bits. During generation, Reed-Solomon recovery code words are calculated from groups of data code words and added to the symbol. During decoding, the surviving pattern can be checked against those mathematical relationships. Within a block's correction capacity, damaged code words can be reconstructed. This is redundancy, but not a second visible copy of every missing square. Standard QR code offers 4 selectable levels: L, M, Q, and H. Denso Wave describes approximate restoration of 7, 15, 25, and 30% of total code words. More correction adds more redundancy, leaving less room for payload at a fixed version and sometimes requiring a larger symbol. There is no universally best level. Now test those levels with one controlled message. Every symbol uses the same benign plain text. Version 3, a 4-module quiet zone, and the mask selected by the same encoder. We change only the correction level and the centered white block. With a 7 by 7 center block, level L failed, while M, Q, and H returned the exact text. At 9 by 9, only Q and H returned it. At 11 by 11, only H returned it. Then the 13 by 13 block exceeded every level in this exact test. That progression is useful, but it is not a new consumer specification. The number and arrangement of data and recovery code words can differ across versions and levels. The visible pattern also changes with the payload and selected mask. Our result comes from clean, lossless images. A printed code adds focus, glare, perspective, contrast, compression, and module size limits. Location creates an even sharper limit. Our 11 by 11 block covers 121 positions, or 14.3876% of the 29 by 29 symbol grid. Centered, the level H symbol returned the payload. Move the same block over the top left finder pattern, and both selected decoders reported no detected symbol. Same geometric area, different function. The number 14.3876% is only geometry. It does not tell us how many code words were damaged, how that damage was distributed among correction blocks, or whether essential function patterns survived. That is why level 80's approximate 30% code word figure cannot be converted into permission to erase 30% of any visible region. This also explains why a centered logo is not automatically safe. It consumes some unknown part of the available margin, and its result depends on the exact symbol, level, size, placement, print, and reader. Our experiment uses a plain white square, not a logo, so it does not certify any branding layout. A reader can also fail before any correction happens. Crop the quiet zone. Make the modules too small for the camera. Add blur, glare, low contrast, or steep perspective. The symbol may be clean in its data region, yet still be impossible for that reader to locate and sample reliably. Recovery math cannot repair an image that never becomes usable code words, and different decoders can make different decisions near the limit. Our primary results come from zxing-cpp version 3.1.1. Apple Vision independently agreed on the clean H symbol, the successful 11x11 center case, the Finder region non-detection, and the 13x13 center failure. Agreement strengthens those selected observations. It still does not turn them into a promise for every phone. One more boundary matters. Error correction can recover the encoded payload. It cannot tell you whether a decoded website, payment request, or login is legitimate. A successful scan answers a data recovery question, not a trust question. Inspect the destination before acting. So how can a damaged QR code still scan? First, the reader finds and samples the grid. Then, it extracts data and recovery code words. If the damage stays within the usable capacity of those blocks, it can reconstruct the message, but damage the structures needed to find the grid, or exceed the correction capacity, and the scan fails. This code was designed to survive some damage. Next, we will examine a package feature designed to do the opposite, a bottle ring that should break once and preserve the evidence.